Okay, well, our first speaker today is going to be Jeffery Reedy. It's a pleasure to introduce him. I joined the supervision of his project later in the day, and any professor, I think, always hopes to see their student exceed them, but I had the opposite. Jeff had already exceeded my knowledge of this subject before we even began. So it was great to see the development of his ability to help me understand what he'd been doing throughout the semester. Because the real scientific direction of this project came from our very own Mike Jones. And Mike, do you want to speak on his behalf?
Well, I mainly just want to say, those of you who've been here for a while, this is your third student you've seen do studies of the guitar pickup. But, you saw the first two. Jeff's gone way beyond where they've gone. And he set a very high bar. I anticipate in about a year and a half or 2 years, we're going to have another student who wants to study the electric guitar pickup. And then I'm going to show him what Jeff has done. And we'll see what they think of, see if they want to continue the project, because he's done an excellent job. And I think you'll all figure that out when you hear him talk.
Okay. Hi. My name is Jeff Reedy, and I'll be presenting my physics capstone project, experimental characterization and finite element modeling of a single coil pickup. My faculty mentors are Drs. Target and Jones. In this research project, we will explore the relationship between coil materials, magnets, and magnetic fields on the electrical signal. We will also explore finite element simulation to simulate a sampling of pickups. And by measuring the characteristics of the pickups and comparing them with the simulations, we can determine the validity of computer analysis in design. So what's a pickup? That's a really good question. And I kept asking myself that over the course of this research project. But guitar pickups are transducers. And transducers are devices that convert energy from one form to another. And in this case, mechanical energy from a vibrating metal string into an electrical signal. The transducer pictured to the left is referred to as a single coil pickup. So all sorts of devices act as transducers, like LED bulbs used in your home to your cell phone. In addition to the single coil pickup, we'll be examining the lace aluminotone pickup. It has a very interesting design, and it's worthy of including in this study. So here's a video clip of a strings motion on a classical guitar. And we can see that the strings motion is two-dimensional and is always in the direction of deflection. From a player's position, the motion is actually parallel and vertical to the surface of the guitar body. Strings are made from a ferromagnetic material, usually nickel or steel, and steel. And in the presence of an external field, become magnetized, and these moving magnets induce voltage in the coil. So I want to introduce you to our methods of analysis in three parts. First, we begin with the electronic characteristic analysis. Then we do an audio analysis, and finally a computer simulation with console multiphysics. So starting with the electronic characteristic analysis, the testing environment consists of a computer, a DAC, a test coil, and a pickup for analysis. We use a function generator that sends frequency sweeps to the test coil, where the signal is converted into a magnetic field, and the magnetic field is received by the pickup and converted back to a voltage and measured. We can measure physical quantities such as inductance, capacitance, output level, phase, and resonance frequency using a program called Digilence waveforms. And we can also measure other characteristics such as frequency response and noise floor using a program called Rightmark Audio Analyzer. So starting with the three most conductive metals in the survey, which is aluminum, copper, and silver, we normalize to copper. And as you can see, aluminum is less conductive than copper, while silver is only marginally more conductive. The testing was conducted assuming wire of the same length and diameter. So what we see here are our captured data resonances from our sampling of pickups. These resonances are in the region where human hearing is most sensitive, which is between the 2 and 5 kilohertz region. Incidentally, this is also the range of frequencies resonances from violins reside. And additionally, depending on pickup placement, You want to choose your resonances accordingly. So near the bridge, perhaps a lower resonance, near the neck, a higher resonance. Here, we see the noise floor of each of the pickup in our samples. It's kind of hard to distinguish individual pickups as they all perform similarly. The big takeaway here is that they all behave like antennas and pick up noise, especially power line electromagnetic interference at 60 hertz with all its harmonics. And this is our general frequency response curve of our sample set. See how the audio interface sees the signal. This graph gives us a pretty good performance profile for each pickup in our sample pool. So let's look at magnets as a means of increasing output. In this data plot, we see the output in accordance to magnet formulation. So as the composition changes, we see more output and slight shifts in the resonant frequency to higher frequencies. And notice that as the output increases, the curves become more narrowed and peaked. Now, imagine this orange line as the expected input level from the amplifier's perspective. As you can see, those magnets with higher output will push the amplifier more to saturation quicker, often referred to as overdrive. And depending on your style of music, this could be a desirable characteristic. So for the audio analysis portion, recordings are made from a microphone and directly from a pickup for the playable notes E2 and E4. They're tracked into a program named Vegas Pro as WAV files. And we bring WAV files into MATLAB to produce spectrograms. And we use spectrograms to visualize amplitude and frequency versus time. Now, I can't show you all the spectrograms. There simply isn't enough time. But instead, I'll show you spectrograms from two of the extremes in our pool, the copper pickup at 7.6 kilo ohms and the lace alumitones at 5 kilo ohms. And notice that the energy levels in the high frequency range for the copper pickup, it's quite noisy. And if you could look at it in comparison to the microphone spectrogram, you can see that there's a lot more energy in terms of what's being displayed in the spectrogram to the right. So if we look at lace alumitones, the pickup appears much quieter in this region with the loss of harmonics that's most noticeable above the resonance of around 4.8 kilohertz. So moving on to the computer modeling, in COMSOL, there are many different models of coils to build simulations on. All the models differ greatly on what properties they can simulate and how much compute power is required. In this project, volumetric is reserved for the lace primary coil. And for multi-turn coils, we use homogenize in order to conserve compute power. So for the single coil pickup, we can simulate and map the magnetic field. When incorporating a steel string in our model, we can see how the magnetic field permeates the material of the string. So let's take a little bit closer at the coil and see these connections of the field lines completing the magnetic circuit. As you can see, the intensity of the field in the false color map localizes the region in which the string itself becomes magnetized. You can imagine that these points moving in space produce the change in flux needed to induce voltage. And this cross-sectional area profile is very narrow for single coil pickups. So moving on, let's look at the magnetic field for the lace pickup. You'll notice that because of the two magnets, the geometry is a lot more complex with many points of connection of the field lines with the string. The region of the string that becomes magnetized is much wider, producing a much wider cross-sectional area profile. And to really show you how different these field maps are, we can view the scalar potential. And in this sliced map, we can see the interior region of the magnetic field. So which produces more signal? So if we can imagine a vibrating string above the pickup and then draw a volumetric region, we can see that the design on the right has a much larger cross-sectional area to sense more of the mechanical motion of the string. In essence, greater flux is produced and more signal is generated. The P90 single coil pickup is constructed with this thought in mind. And not only can we visualize the magnetic field, we can visualize other things, such as the current movement on the surface of the primary coil of the laced pickup. And there's two circulations with the greatest density at the link where the secondary coil is connected, so right about here. For the false color map, dark blue represents regions of low density of surface current, while lighter regions showing greater density of surface current. Now, suppose we change the material from the manufacturer's aluminum, say copper or silver. Surface current density from aluminum to copper is markedly increased. From copper to silver, the difference isn't nearly as pronounced. And as we look at the simulated data, this will have a little bit more significant meaning. So what does the data say? So the table on our left is our measured results. And in the middle is our COMSOL estimates. And on the percentage error is in the table on the right. And what we see is that between our fit curve and our COMSOL estimates, the model produces pretty decent results. And we can go on, I feel so comfortable with making predictive values based upon the modeling, is we can predict that a single coil pickup constructed from aluminum wire with the same gauge and the number of turns adjusted so that the resistance is the same as the copper pickup would have an inductance that is about half, and the resonant frequency is much higher. So I want to make a note here is that as the number of turns increases, the resonant frequency decreases and the output increases. So this is just a little animation kind of showing that. It's not showing the increase in amplitude. Couldn't do that in PowerPoint, unfortunately. And if we look at our output at resonance, here we're comparing the measured results to the COMSOL estimates. Again, we get pretty good results. And we see that a pickup that's constructed from aluminum wire would produce about half of the output at resonance. In addition, if we change the primary coil material from aluminum to copper, the output is much larger. Silver produces only marginally more as output as compared to copper. And this is expected from when we studied the materials themselves. So what does the data suggest to increase inductance and hence output? The key point here is that this is an optimization problem, and we want to increase signal output with less noise, and this is really a balancing act. Guitar pickups act like antenna, and they induce voltage from radio and power-related electromagnetic sources, and this creates what we often see as unwanted output or noise. The data in general suggests that coil materials can contribute to signal output, and it doesn't. The material itself doesn't contribute wholly to inductance, but when used in conjunction with point 2, number of turns, it can. So if you choose a wire with less resistivity, you can get more turns out of it, and that would increase inductance and more output. Adding a core or changing core material can increase inductance. So a core that's more permeable with more iron would increase inductance. And for the case of the single coil pickup, replacing the 6 pull pieces with a solid bar magnet would greatly increase inductance. And then the cross-sectional area of the coil will increase inductance. And then, of course, magnet selection can increase inductance and output as a result. So this is a photo of a supercomputer at NASA's Moffett Field facility. And believe me, I sure could have used one of these while I was working on my own simulations. Simulations are extremely useful in gaining insight on how pickups work as a physical system. Additionally, we can tweak just about any parameter and see results almost instantly. And But as useful as they are, they can be inaccurate and require some degree of reworking. And I found in my own research, as my understanding of the problem changes, so does the simulation. And some models used were far too complex for the software. So depending on the purpose of the simulation, I often had to break them down and simplify them further. But once a model is constructed, we can simulate performance characteristics for a model pickup. And we can also simulate for materials that cannot be easily prototyped due to cost or availability. So that's pretty much it for my capstone project. But I wanted to, and I want to say thank you for joining me here. But I wanted to leave you with this satirical look at the music industry, where the protagonist, Christopher Guest, in an interview makes a point in which the amplifiers they use are special because the numbers on the faceplate goes to 11. And when the interviewer states, "Why don't you just make 10 as the loudest as the amplifier goes?" Christopher Guest stares blankly at the amplifier and for a moment while chewing gum and says, "Well, these go to 11. So go out into the world as physicists, turned all the way up to 11, of course.
All right, let's begin with some questions for Jeff. I'm looking for hand raises. I'm not seeing any, and maybe it's the same thing for me where I have difficulty with this. So I'll look for it visibly or in here. But I had one. I was just shocked at COMSOL being within a fraction of a percent. That modeling was very impressive. But so I'm wondering, like, does that mean a toy model, a diagram of it? Would that get you fairly close, or do you think, especially with the lace pickup, where it's not a winded set of coils and a magnet, the lace pickup, I wouldn't, it would be hard for me to start that process of imagining those physical parameters of it. So could you talk a little bit about when you got the COMSOL results and whether you expected to get anything so remarkably close to the actual measured values?
Okay, so what I had to do, at least, especially for the lace, is I had to break it into smaller pieces because the application itself couldn't handle it as a whole. So I had to measure the outside frame, its inductance, its resistance, and so forth, and compare it. And so initially I had created the model in COMSOL, and it was kind of somewhat close when I compared these individual parameters to one another. And it required a little bit of tweaking. So what I found is in COMSOL, they'll give you like 100 different choices for silver material, for instance. And I had to place a pretty good guesstimate of what materials that the pickups were actually constructed from, and then run the simulation again. So I would say, okay, well, this one wasn't even close. Let me try a different material until I got the materials dialed in. And that was pretty hard considering we didn't have the Keck lab available. So I couldn't do any material analysis for just the materials used in the product. Ryan, Mr. Brown was quite integral of getting some initial measurements for me. I had sent him some sample wire, and when he was in the SEM lab, he was able to make those measurements for me. So I had a pretty good idea of how large the wire actually was, and that kind of helped. That really helped hone in the model quite a bit more because I can use those exact measurements, or I should say, sampled measurements. And so as I kind of dialed things in, the measurements became a little bit closer and closer, and then I was pretty good with the results at that point.
Yeah, very, very impressive.
And,
Let's look.
and, and the thing is I actually had to feed it from one part of the model into another part, because again, it couldn't handle all the sections together in its entirety. And it depended on what it is that I'm looking at, right? So if I was looking at the electrical characteristics, it was like, nope, not having this. Sorry, can't compute it. I'm going to crash on you. And so then it's like, okay, well, I'm going to just take this part of it. I'm going to compute this part, and then I'm going to feed results into this other part. And that allowed me to get some simulated results.
Very good. I see Alex has a question.
Yes.
Yeah, and just I think since I'm a co-host, there's no hand raising function, in case you're wondering about that, Scott. So, so great talk. Thank you so much. I had a question. I was just thinking about, like, if I were like a business person trying to build these. Of course, you want you know, the best device possible, which is mostly what you were studying, but you also would want to think about like some like cost benefit analysis here.
Mhm.
I'm curious, like, did you find anything where it's like, this is actually the cheaper material and it was better? Or was it like more expensive material was always better?
Okay, so yes, that gets right into the economics of the situation. So what I found is that most manufacturers, they kind of set on copper. And there's a really good reason for this. Tooling 42 gauge copper, which is very, very, very small diameter. It's like smaller than the diameter of the shaft of your hair, right? It works out to be 0.0005 cents per foot. So it's the cheapest material that isn't that's mass produced. So when I initially had gone out and I was going to build these coils myself, I actually priced these out. I went to, I think it was MWS Wire, their premier wire source on the West Coast. So if you're going to buy bulk wire, this as a manufacturer, you would go to this company. I found that what they told me was tooling aluminum wire at 42 gauge was very difficult. They didn't have equipment necessarily to do that, and they would literally have to rejigger their machines to accommodate that order. And the pricing worked out to be roughly $1,200 for a pound of 42 gauge wire, and that's just $1,200, right? It's quite a bit expensive, and per foot, you know, that worked out to be, I think it was like about $1.20 a foot, right? So then you have the other part of the problem, which is silver. For instance, silver has greater conductivity, but the problem with it is that the material is based on commodity pricing, and I think I checked it yesterday. It was around $32 a troy ounce, which meant that when I priced out that material for the same kind of spool as the aluminum wire, it worked out to be around $7,000. So so it was much cheaper to buy the manufactured wire or the manufactured pickup with the silver wire, because they could buy it in such large bulk, right? But it's still, you know, they price it accordingly. So the copper pickup was priced around between $43 for just the finished product, whereas the silver is priced around $250 to $300 per unit. And it doesn't necessarily, it alters the sound a little bit, meaning that the resonance frequency is a little bit lower because it has more turns, but it doesn't produce better frequency response, is what I'm saying. So from a cost benefit perspective, a guitar player would be well suited just to buy copper pickups, and depending on the purpose of their playing, they'll purchase it in accordance to output level.
Cool, thank you. Yeah, I was just curious about that, so I appreciate that.
Thank you. Hung Tao, I see your hand up, so please, but I will remind Jeff and Hung Tao, we should be brief so we can hear Trent's talk as well. So
okay, all right, yeah, thank you, Jeffrey. I think this is a wonderful job work they did. And my quick question for you really is, how big is the surface current density? Are we really talking about milliamps, microamps per centimeter squared? And you also mentioned some capacitance. What's responsible for the capacitance that you calculated or measured in your work?
The capacitance, that's a good question. So the measurement was based upon where the resonance frequency was at. So I can calculate backwards where the capacitance would be. Are you referring to from the simulations perspective? Because right. I really didn't jump too far into that, simply because the volumetric models didn't support computing capacitance in that way. So that's one of the drawbacks from, let me see if I could find the specific, yeah, so that's one of the problems with the homogenized, because I can tell it that it's 5,000 windings, but it's not able to say, okay, well, it's 5,000 windings of 100 across and 100 up, right? If I wanted to study that, I would take a cross-sectional area, or just slice it where it's a small dx, and just say, okay, well, this cross-sectional area, I can assign these bits of wire, these round bits of wire material, and I can compute things like skin effect, capacitance in between the wires, that sort of thing. So this is kind of one of the real drawbacks, depending on how you choose to model it. You kind of have to fit with the limitations of what, like homogenized, it just doesn't compute capacitance. It's just not able to do that.
Okay. Yeah.
Volumetric could, but you would have to literally have to do 5,000 turns or 10,000 turns.
Well, let's thank Jeff again. Let's get those claps going and the emojis. Very good.